Morning. So in this video, we'll be discussing wind loading. So this one here. So we're done with all these, but the wind load. Um, so, oh, by the way, from last video, I said that I will show you a framing plan with the pending load. So this one. So this is from a project. I think um, it was before COVID time, so it's been a while. So this is a roof framing plan. Now, if you noticed, I have this diagram because this is important for the um, joist. So this framing is using the open web steel joist, and for them to size the appropriate um, section like depth and um, stiffness, they need all the load information, and this is the bonding load diagram. So for this particular framing, this is this is lower roof. So this is the lower roof. Basically, what happened? That's why the bonding load is quite high because this is the framing. We'll just do like a skeleton. This is an irregular shape structure, but if you look at the elevation for the section, this is what it looks like. So there's a height difference here. Now the problem on this one, or not really a problem, but the situation is the mechanical engineer decided to run or not the it was not the engineer. I mean, well, it was the mechanical engineer, but under the requirements of the architect wanted to have all the rainwater leader or downspout um, basically from the upper roof down to this lower roof here. So what happened is all the water from this all discharge from that roof will be carried by the lower roof. In this instance, that's why the bonding load on the lower roof is quite high, 2.17 um, kPa. And then this one, this is from, now imagine this is the upper roof. Now the upper roof, the lowest point is only 1.6. This one is 1.24 for that roof because this is like an irregular shape, like a Avengers logo. That's the shape of the, or close to it, shape of the of the building. So if you noticed, in the upper roof, it's only like zero point 0.4 from the edge, and then 1.6, but in the lower roof, because a portion of the upper roof drains into the lower roof. So that's why this one is much higher. Then you compare that to the um what do we call this one? The snow drift. You compare that one with the snow drift loading, and whichever governs, then that would be the final load in sizing the joist. So yeah, again, for flat roof, bonding load is also considered, and sometimes that's the critical one. Um, I've read a paper on this one, why bonding load is crucial for flat roof, because there's already like an structure here that collapsed, and then um, after investigation, it was found out that it was the panding load that basically governs. It's near the coastal area, so snow load is not that high, but the panding load is, so the portion of the roof collapsed. So that's why you have to consider that one. Anyway, so like I said, our discussion for today would be focusing on wind load, and we will discuss or at least I will show you like how wind loads are calculated, the main wind force resisting system loadings versus the components and cladding, then how is it applied to a structure. Now, in this particular video, we will use the sample. This design guide, I posted this in our group, this one here. So this is, well, I'm familiar now with the Canadian code, so that's why I'm using this one. But the theory would still be the same. So just look at your local codes and see, like, criteria for calculating the loads. If it is open structure, well, in Canadian building code, the category is divided into three, like category one, category two, and category three, depending on the opening sizes of the building. But in the ASI 7, like US standard, you have to consider it's partially or it's enclosed, partially enclosed building and open structure as well, I think. So yeah, this design guide, it has a uh, so this is the sample calculation. So it shows this is for uh, this sample is for pre-inch building, pre-engineered building, and then it shows how the loads are calculated for, like this one, how the loads are applied for the structure, for the cladding, for the purlins. So I will try to show you how I analyze the or calculate the wind loads using this sample as well. For you to fully understand this design guide, you have to um, read this one in conjunction with the National Building Code of Canada, because all the provisions for wind loading, especially in the commentary, um, everything is explained there. This one is more of like a have a sample building and then get the information from the building code. Although it is tabulated also, it is shown in this one here, but this is more of basically just pick up from the code and then just paste it here, like summary. But the table, the calculation, it's in the building code. So this one. So the sample here is, so there is a sample here, and then the location is, where is it? Uh, description, appendix C. So yeah, here this is in appendix C. This is where the climatic information, like all like loading, like snow load, wind load, rain load, um, like freezing index. It's in the building code, appendix C. And then this is the formula for calculating the pressure, internal wind pressure, the external wind pressure. And then there is a sample here. Where is it? So this one. So this sample calculation, this is for a building um, in Moss Jaw, Saskatchewan, 20 by 50 meters long, 8-meter eve height. And then it has all the conditions like, so this one especially like, assume the building is not located near a hill or escarpment. So this escarpment, I think this is the KZ in the, is it KZ in the US code, the ASCII 7. But this is basically, I created a spreadsheet for this one. This diagram. It's in the ASCII 7. I just can't remember like the term used in there. But you have to first, like when you analyze the structure or the building for wind loading, you have to determine if it's in a hill or escarpment, so that you will know if you have to increase the topographic factor, this 1.2. Now, I mean this is just a sample building, but if it's not located in a hill or escarpment, there's no escarpment, then your where's the PDF? So your city would be 1. That's the minimum, and then importance factor is for wind for this building. This is a normal importance, so that's 1. So this one, um, the only thing that I don't understand in this particular calculation is he rounded off the value of the exposure factor from 0.96 to 1. It's not written in the code that 1 is the minimum, but I mean, in this example, I mean, if you increase to or make it 1 instead of 0.96, you're just being conservative and it increases your wind pressure. So this one, because of course, like every start of the design, you will do all of this load calculation. So I created a spreadsheet and then I already changed all this information to Moss Jaw, Saskatchewan. And then this is this shape of the building, 20, I think this is 20, 50 by 20, 8-meter. Now, in the wind load, so this one, in this example, um, he calculated this one here first is the wind induced, or this one, internal pressure on the liner sheet. Now, in the building code, you will see this kind of interior pressure liner sheet. So you will see, oh, it's not shown in there, but you will see this kind of figure like this one diagram, and then for cladding, this one here. So for components and cladding, the surface like the CPCG pressure, like the pressure coefficient, is different for components and cladding versus the main wind force resisting system. So in the question now is which one you will use now. Of course, if you're designing for the roof cladding, the purlins, that's obvious because that would be under the components and cladding. But for example, if you have trusses, the question now is it under components and cladding or mean wind force resisting system? So in these documents here, um, in this one, so this is under this one. This is under the frequently asked questions. This is found in the guide to the wind load provision of ASCII 7. Um, I don't know in other, like this is really old version. I think there's already ASCII 7.22, but this is really old copy, and I don't have I haven't put the um, the new design guide. So this one, the question is, when is a gable truss in house part of the MWFR system? So the idea here is the roof truss itself, if it is um, the area, there's an area requirements like this one here is from AC7 also, chapter 30. I think this is also found in other chapters, but there's this minimum design wind pressure, which is 16. And then this one here, if the tributary area is greater than 700 feet, so for example, if you have a truss and then, or a house, this is your framing. Now, if this is wood frame, like especially in North America, the way we frame of trusses, these trusses are like 24 inches on center, so that's obviously part of the that will be a components and cladding. But if you are talking about pre-engineered building, if you are talking about pre-engineered building where this is your columns like that, and this is typically between 20 to 25 feet, and then this is like typical so far in all our projects, like for pre-engineered building. um, I design, well, for pre-engineered building, like for shops where they are using pre-engineered building, our scope is just the foundation for structural, because the pre-engineered building is already designed and manufactured in other, you know, the other company. Um, Most of the time, um, the pre-engineered building supplier is from the United States, and then it will just be shipped out here across the border. And this is say 20 to 25, and this is typically 100 feet. Now, if you multiply this one, 100 feet, and then your base spacing shall be 20 feet, so that's already 2,000 square feet, which exceeded oh, the maximum for you to consider whether it's under main wind force resisting system or components and cladding. So that's why for pre-engineered building, it's always the main wind force resisting system. So in this particular example, we will be discussing or calculating wind loads for um, pre-engineered building. I mean, I will show you, but we will also calculate the pressures for, roof and, the roof cladding, the wind cladding, the purlins. So based on our example here, this is the calculation. Internal pressure. So this one. Now this value here, CPI, which is zero point 0.9 and zero point 0.6, assuming this is category 2. Now you have here a calculation. So this one, if you notice, the CPI CGI is negative zero point 0.9, and then the this is the positive, and the negative value is the positive value is zero point 0.6. So in this particular calculation, I separated the CGI and CPI, although in the building code it is clear that um, if the coefficient is given as CG or CPI CG, then you don't have to separate those. But I mean, this is just my calculation. It's at least this gives me an idea what exactly is the CP by separating the CG. Like typically CG is 2.0, so I know what my CP is like CPI and CP. So this one is zero point 0.9. If you multiply just the two, like 0.40 minus 0.45 to multiplied by 2, so that gives us point. Now, so this one negative point. Uh, if you multiply this one minus 0.45 and 2, so that gives us negative zero point 0.9. And then at the same time, zero point 0.3 times 2 is zero point 0.6. So that's this one here, this one. And then of course, based on the calculation, this is your formula for calculating the wind pressure. So it will give us 0.47 for the negative pressure and 0.31 for the positive pressure. Now, in here, 0.47 and 0.31, so 0.37. So this is it? Oh, this is 0.42 and 0.28. I think I remember there is a value that changed 0.90. Let me go back to the CT and CEI is 1, Q is 0.50 to 111, CT is 1, CEI is 1. So this one here, so like I said, in the calculation, he uses 1, but on this one I have zero point 0.5, so I will just highlight this one here, that these values were changed. So if we change this to 1, so we should get the same answer, 0.47 and 0.31, the same as this one here. So like I said, it's not written in the code that the minimum is 1, but for some reason he rounded off the, or round up the value of the CT instead of, like I said, here is 0.96, he uses 1. And then in this one as well, he also uses 1 instead of zero point 0.9 in my calculation. There's a formula for calculating the CE. That's this one here. And yeah, I don't know why he rounded the value to 1 instead of just using 6. I mean, the result would be more conservative, but it's not required. So the next sample is, so basically the negative internal pressure, what it means is if um, just do it here. So in in a pre-engineered building like this one, right? So in the pre-engineered building like that. So you have purlins here, right? So you have purlins, and then you have your roof cladding. Your liner sheet is right in the underside of the purlins. So that's why um also like if you have girts and then you have your wool cladding here, and then your liner would be the purlin. So if you look at girts, um so if you have something like this one, in your girts. So this is your internal liner, and then this is your exterior cladding outside. Now it is separated because, like, if you noticed, um, I have in my uh, in my input, I have here is either the is it composite or non-composite. Now, the difference between the two, I think I already discussed that in my previous video, but for example, you don't have any liner, and then um, typically if you have your purlins here, right? If you have that purlins, and then you have your roof cladding, but this cladding, there is no liner here. um, All internal pressure will be exerted to your roof cladding as well. So in that case, when you design for the attachment here, you have to consider the composite action. Composite action meaning this one is resisting both the internal pressure as well as the external pressure, and then you'll just get the net pressure. And that's the same calculation when you design the or when you analyze the purlins, because the purlins is either if it's the liner is right here in the underside, if it's a non-composite action, but it's the same element that's resisting both pressure, the internal and then the external pressure. That's why in designing the purlins, you always consider the internal and external pressure. Now, going back to this example, now, by the way, for the liner, the positive, so you have positive and negative value, right? So the notation for wind loading, if it is positive, that means it is towards the surface. So this is positive. And now negative is if it is away from the surface. So this is negative. Now for roof cladding, for the exterior one, if that is negative, that means that is away. And then this is negative, and then positive is going towards the surface. So that's why in metal, in pre-engineered building, you will have to consider, you know, both the internal and external pressure. You don't have, I mean, I've seen a post, I will just name him, but the post was like load case, something like that. And then windward only, and then leeward only. So there's no such thing as windward only, leeward only. You have to look at your structure if it so if it's like both resisting both the internal wind pressure and also this one here. It will always the like the windward and leeward. That's just direction. For example, this is your building. When you say windward, if the wind is in this direction, that means your building will be experiencing a windward force, no, and in the leeward, that one, and then the roof, it could be depending on the slope. This could be plus minus, and then this one, there's always negative. So in his post, he said load case one is windward only. You cannot say, or when you apply the wind load, it's always like always together. The leeward and the windward, leeward and windward. These are just direction or which side of the building you are with respect to the direction of the wind. Now, if the wind is coming from this direction, right? So this now becomes the windward. This now becomes the leeward side. So you cannot just select or apply the load windward only and then leeward only, and then your load case three is leeward and windward. So that's not the way how you apply the load. Anyway, so we already have the um liner, internal liner. Mm, oh, 32. Is it the So we already have the internal pressure on liner sheet. So when you analyze the liner, then usually it's the same, like the same metal cladding. Most of the time for industrial shafts, what you put on the external side would be the same on the internal side. Sometimes they will use like some kind of insulation, like a liner, which is also common here. Then you just make sure that the fabric can withstand whatever the pressure is. Like for example, this one. So when you analyze the liner, the negative and positive only indicates the direction of the force. So when you design it, you always size it based on um, for example, uh, so this is your girth, right? And then this is your external cladding, and then this is your liner. Now, when you design the fabric itself, this one, when you design this one or this one here, the cladding, when you analyze the capacity of the cladding itself, then you use the absolute um, value. Say, for example, that was it 0.41 and positive 0.37, right? So when you size the or determine the thickness of this, because the manufacturer will have a load table for their product. Say, if spacing of the girth is, say, if the spacing of the girth is, say, this is 5 feet. Now you will see in a load table like this is your spacing, and then spacing or span. Sometimes they will use a span, and then on this one is the gauge. Is it most cladding um, use 25? Sometimes use gauge 22, but 25 is the most common here. I don't know in other area if the wind load is um, bigger or larger than what we have here, then we would probably need gauge 22. And then there is this, you know, value here, say 1.2 or whatever is the available capacity. So when you size the cladding itself, use the absolute value. So in this case, 0.41 is the highest between these two, because 0.41, that means this is pulling the cladding, and then 0.37 is pushing the cladding. So when you size the cladding, regardless of the direction, always use the higher value. Now, when it comes to sizing the fastener, that's another story. Because if you design the fastener here, you know, like a screw in attaching the cladding to the girth, then you will always use the negative value. Why? Because if this is um, negative value, that means that is pulling your cladding. Then your screw will be in tension, and then check also for withdrawal. But if it is, you know, if it is positive value, that means that's pulling. Technically, you don't need a fastener, right? So that's why you always use the negative value in sizing the fastener. But if in case, for example, the negative pressure is say 0.41, but the positive value is say point 0.5. Now, in designing the screw, it will be 0.41 because that's pulling. But when designing the cladding itself, you use 0.50 because that's the pressure acting on the cladding itself, pushing. So that's the worst condition. That's pushing the cladding. So don't be confused with the negative and positive value. Now, in the next example, like calculation on this one. So like I said, if you follow this calculation, no, I already uploaded this in the group. The group is structural engineering for dummies. No, if you want, you can. I encourage you if you are, new to structural engineering. I would encourage to join the group. Then you can ask questions, or if you are experienced or practicing structural engineer, you can also join for sure, and then give advice to new engineers, like students or those. Well, I would say all engineers, but are new to structural engineering. It's not exclusive for like um, aspiring new engineers, structural engineers. Everybody can join and then share your knowledge, learn at the same time. So that's the purpose of that group. So you can join structural engineering for dummies Facebook group. Now, like I said, when you try to follow this design criteria in calculating, this is not only for wind actually. This design guide covers a snow load as well, dead load. But like I said, in this particular video, we are only focusing on wind loading. It's either main wind force resisting system or the components and cladding. So I would recommend that if you read this design guide, you better also read the NBCC um, code. It is free to download. You can download it. So make sure. Um, sa-
Kay duwa daw sumayor og si Ruel ug di ka busy.
ayun ako trabaho.
Kay trabahon.
Sila na de.
First aid lagi. Ya,
Ay, anya na.
Five.
Anya lang. So you can download the NBCC 2015. So this is free to download. So um, yeah, this one. Just I mean, if you want of course, if you want a hard copy, the binder and soft cover, then for sure you can um purchase it. But if you want the PDF, just the PDF, then just download the free version, the PDF version of it. It's free. And then also, aside from this one, make sure also that you downloaded the part for commentary. So this one. So this structural commentary, this is actually a user guide, and then this explains the provisions in the code with regards to the structural portion of it, part four. So part four is the structural, and then this is the commentary. This is also free. You can download. Like I said, if you want to buy the hard copy, then you pay $45. But if you want the PDF, then just download the PDF. We have a new code actually, 2020, or I mean 2025 is not yet in effect. 2020 is the latest one. But in this particular design guide, because that is based on um, NBC 2015, then you download this structural commentary 2015 as well as the NBCC 2015. The only, the only, it's not a problem, but I was, um, how to describe it, not angry also, because what happened was I was making a spreadsheet for seismic calculation based on NBC 2015. And then I only update my spreadsheet when I'm not busy. So when I was about to finish my spreadsheet, it happens that the 2020 took effect, and for some reason the entire seismic provision was changed. Because normally, for example, if you compare the 2020 05 2010 and 2015, it's the same calculation. But in 2020, it changed everything, like exactly, like totally, like completely different calculations. So everything was, I mean, it's not wasted because also, I was still, I mean, I use it in other projects and previous projects. At that time, I was just trying to, organize my calculation, make it more presentable. Then the code changed and everything changed. So, but like I said, since this design guide is based on 2015, so just make sure that the building code that you will download is also the same, like 2015. So anyway, so this one, when induced pressures on roof cladding. So this one, the first one is the liner, that's the underside of the purlins, and then the um, pressure on the roof cladding. By the way, this is the components and cladding pressure, not the MWFRS. So again, CE is using 1.0. So go back to our calculation, this one here, if I will use this, 1, I will change this to 1. And then this is also 1. Now, in the example, the calculation is the same. It's just the change is on the pressure coefficient CPCG. And then you have different calculations here. So for example, for area R, R is where is R? 0.26 and 0.94. This one, the bigger area, that's R. Let's look at this one here. R is the bigger, the white one, and then the S is the hatch area, like diagonal, and then the solid one is the C. So that's the solid one, C. Can we zoom this one? Yeah, so that one there. So S is the hatch, like diagonal hatch. Then R is the common area, and then S is, or C is the uh, um, what we call this one, the um, area, like the common area here, and then the black is the um, that would be the biggest, I would say, the most push, or I think the biggest wind pressure zone. C, yeah, C. So the pressure at this hatch area, the solid one, that's way bigger than the normal pressure. So that's why I don't know if I can find. Let me check. This is also this is a flat roof. I don't know if I can. I managed to download it. No, it's not here. So anyway, what they did was, I mean, when I look at it, I was with another engineer, my trainee, and then he was confused what it was for. But I grew up in the province, and I know exactly what was that for. So um, so when we did the inspection, this is flat roof. This is a flat roof, and then right in at the corner, at its corner, right here. Oh, it's weird. Anyway, right at the corner here, you will see like concrete pavers. That's concrete blocks. Yeah, concrete blocks or concrete pad. They call it concrete paver here. This is typically 2 inches, and then this is I think this is 12 by 12 inches or 16. So 2 inches thick and then 12 inches width and length, and it is placed right here at the corners, right here. And then I asked the I asked my colleague, like, do you know what's that for? And then he has no. But me, I grew up in, I grew up in the Philippines, and in the province, it's really common. So basically, this is a counterweight, and then this will resist the uplift. But in our case, every time there is typhoon, we will we will put. So this is, I mean, common roof type. There is heat roof. So I don't know. You probably see this, but in the province, when there's typhoon coming, we will put counter with it. But here, we'll use sometimes bag of sand or tires, used tires. So that is to counter the uplift on the roof. So that's what's basically the explanation for that. I mean, at this time or before, I don't know exactly. I don't know that the wind pressure for each um, or a specific location on your roof is different. I just I just know that every time there's typhoon coming, we'll just put the counterweight in there. But this one is more of a clear, location where you want to put your. So if there's a typhoon coming, if you look at this diagram, just look at this, hatch area, and whenever there's this solid, like black solid hatch, then that's where the biggest pressure on the roof. So you better put all your, or not all, but most of your weight on that particular location. So on this one, the so for R, that's 0.26 and 0.94. And if you look at here in the spreadsheet, 0.96, 0.26 and 0.24, this one for zone R, that one. And then for zone S is 1.3 and 0.26, 1.3 and 0.26, this one, right? And then for zone C, 0.26 and 2.81. Imagine the difference. This one is 1.3 and then this one is 2.81, more than double. So the pressure right at the uh, this one here, roof cladding for gable. Um, this one here, I was looking at different. This is if the angle is between 0 and 48. So this is hip. This is gable, this is hip and gable. So this is where is this hip in this angle? Hmm. Why is different? The angle is point. Oh, this one here. For this one for slope with for a roof with slope of 7 or less. Yeah, because our slope is 4.76. So this is the diagram. So I will show you how to read this. I mean, if you noticed in the sample here, you don't see. You only show this calculation. I think this is also a table here. Yeah, and this one here it only gives the what we call this one, the coefficient itself, like this 1.5, the REC, like a zone depending on this building category. Like I said earlier, like it depends on the category. Is it 1 category 2, category 3. And in that category, you can find it in the commentary what it is. What is category 1? What is category 2? Category 3 is more of, it's an open, it has a large opening, and then it will remain open during a storm. And then category 2 is it has a large opening but will be closed in the event of a storm, something like that. And then, so going back. So actually, each each element have this, for this particular like cladding, it has this diagram. And what you need to do is, this is the CPCG. Now you will see, so tributary area for roof and for roof cladding, the area required is let me see if we can copy it here. Okay, so this one. So what you will do is, usually, like I said, it depends on the area. Now, if you notice, um, at a 10 square meter, this is now like flat, right? So it won't change regardless of the roof area. It will be the same. The smaller your area, the bigger the, because this is 0 and then this is 1. So the bigger the area, the bigger the CPCG, or the smaller the area. So because the coefficient is more of like an average. So that's why for roof and cladding, it assumes a area of 1 square meter. And then all you have to do is just project that line. And then wherever it intersects this one here, then you draw a line going left, and then you will determine what is the um, value. In this case, looks like this is point 0.5. Now for area, if you're, for example, if you design a roof purlins and then you want to be specific on the area to or specific to get the CPCG, then you calculate the tributary area, and then say if the area is between, let's say, 4, then you project it here, and then you project it to the left. Then that is your what we call this one. That is your CPCG. But usually in even in this example, I think it will tell you that it assumes this one coefficients are based on a tributary of less than or equal to 1 square meter. So that is the assumption if you are designing a roof cladding. So on this particular one here, cladding, so roof cladding, you have 0.26 and 0.94. So let's go back to our calculation. Roof cladding. So that is this one here, 0.94, and then for zone S, that is 0.26 and zero point 0.3, point 0.26 and 1.3. Is it 1.3 or 0.3? 1.3. So this one here. I have this automatic conversion from KPA to PSAFE because all these calculations are in metric, but I need a imperial. Like, all my calculations are like in design. I'm using the imperial unit. I'm used to it, so that's why I have this automatic conversion. So I don't have to, convert every time I do a calculation. So I mean, it's done in Excel, so why not, right? So for the zone C, so 2.81 and 0.26, so this one here. that one. Now, if you notice, I have here a different, what we call this one, different table here, which says composite wind pressure. This is non-composite. This one here is non-composite. But like I said in what I said earlier, that if your structure, mm, if your cladding is um, the same as like you don't have a liner, and then everything is acting on the same element, the same roof cladding. So, for example, there is no liner sheet. So that means that is now a composite action on your um, cladding. Mm. Uh, so that is not composite action to your cladding. So you have to consider this one. You have to add the CG, CP, and the CGI, CP. But remember, or make sure that you are not adding the positive to positive, and then add the negative and negative, because that's completely the opposite. So for example, like I said, this is your purlins, right? This is purlins, and then this is your roof cladding, assuming it's a composite action. So there is no liner, so all forces, external and internal, will be acting on the same the same element. So the negative value for external, the negative is going away. So this is negative, and then the positive is going towards the surface, right? Now, this is for external pressure. Now, for internal pressure, the positive is going this way, right? So this is positive, and the internal negative is going away. So this is negative. That means when you analyze or size the cladding as well as the connector, you will add now the negative external and the positive internal, because it's going in the same direction, right? So you add these two because they are going in the same direction. This is going away, this is towards the building. And then also add the positive external to the negative internal, because it is going in the same direction, right? So do not add positive external and positive internal, because they will not cancel out because they are not the same value, but you will get a smaller number, right? So negative, again, negative external and the positive internal. You don't separate these two if it is, if it is what we call this one, if it is a component, composite action, like in our um, framing, like when you say in our framing back home in the Philippines. So this is common, like this is truss, right? So you have your roof here, but you have also a ceiling. So in this case, you don't do this addition and subtraction, because your roof cladding, that's different, because any internal pressure will not be acting and like below the roofing, because you have a ceiling. But if you don't have ceiling, no, if you don't have ceiling, that means your internal pressure will also be acting on the roof. So just make sure that you account for that one. So I hope that is clear in this particular. Um, by the way, this hidden line, that is for if you have overhang. This one OR, OS and OR. and then OC. O means overhang. So if you have overhang on your, for example, this is your roof, but your wall is only right here at one, then that would be, I mean, it doesn't mean that this value coincides with the wall line. That's not what it is. But what I mean is, if this is your roof outline and then you have overhang, that means your wall is offset inside. Then use these values here for the overhang portion. Anyway, so we're done with the roof cladding and the internal liner. So what's next? So the next one is roof purlins. Now, basically, this coefficient is you only add the external and the liner. That's what it is. But this one here in the in my calculation here, like for example, on this one here is 0.62 and 1.9 for the zone R. So 0.62 is uh, basically, like I said earlier, that you only have to add. Um, that's why it's easier if you do in a spreadsheet because all you have to do is just supply the input, the location, and that's it. A building size, that's it. So on this one, Portlands. Where's my Portlands? This one here. So on zone R, 0.98, 0.98, and then the only difference here is for Portlands, the assumed tributary is 10 square meter. But like I said, if your tributary is less than that, if you want to be more specific, all you have to do is look at the graph. No, this is the same graph, and then uh, because what happened, so in for what we call this one for purlins, because it assumed at least 10 square meter tributary. So the value of S, C, and R is much lower than the components and cladding. But the calculation, how you arrive the value is simply the same calculation as this one. You just add the two. The only difference is you are now using a tributary area of 10 square meter, which is which will give you a lower coefficient of CPCG. So basically, this from this calculation, you have 0.62 and 1.9. 0.62 and 1.9, is it the same, this one? Again, this one, if we change this, so this is 1, this is 1, 0.62 and 1.9. Is it the same? 0.92, 0.62, 1.9. No, this one here. So that's the same. And then zone S is 0.62, 1.35. Now, if you notice, the positive value is the same for R, S, and C, because diagram, in the diagram, tributary area 10 square meter above, that's flat, so the same. So S, R, and C are the same. So that's why um, you will notice also that it's the same. So if your tributary is say you have bigger spacing, bigger tributary, bigger span for your pore lens, and then it will end up say 15 square meter. So it's the same, but it's always conservative if you use a smaller area. But you know, it's up to you. But the code says that if you are designing for the roof cladding in liner, you use 1 meter or 1 square meter. But in your roof pore lens, you assume 10 square meters area. If it's in between, then you use this, you know, linear um, interpolation or what do you call this one? Similar triangle. So by ratio and proportion. So going back, so this is 0.62 and then negative 1.35. This one, negative 1.35, and then the same 0.62 and negative 0.45 to area C. The same. So again, I'm not sure why he used 1 instead of the actual value from your calculation, but it's just more conservative that way, which is fine. So that's Portland. So basically, like I said, that because the Portland supports both the internal. So for example, if you're even if your this is your pore lens and then your external pressure is right here, your roof cladding, and then you have internal liner. But both the roof cladding and the internal liner is supported by the same element, this one. That's why you add the forces between the two. The only difference between the separate calculation of this one because of the area being considered when you design the pore lens. That is why it's much lower if you add the individual pressure of the two. So, uh, so that's for the pore lens, and then wall cladding is the same. This one here. So there's also a diagram. Now let's go straight the same as wall girts. The wall girts also and the the pore lens the same. You assume a 10 square meter. Now let's go to this internal um, frame loading. Now how the loads are applied to this one. Now, if you noticed in this area, I would like for this particular example. Let's just or let's just look at the individual pressure first. So for this particular building, CPCG interior frame. Area 1, area 2, area 3, 139.75. Is it? I think it's adding the internal also. Because this is used for the primary. So when you analyze the frame, this one for this particular um, element, because it now the tributary is now exceeding 700 square feet. This time you have to use the that's why you have to use the what we call this one, the um, main wind force resisting system this time. And 0.39, 0.75, 1 is 0.75, 1 is 0.75, is 1. Okay. So CPCG is 0.75 for area 1. And then for because this is interior frame, so one is 0.75, and then area two is 1.3, negative 1.3. This one, area 2 is negative 0.3. Let's highlight that one. And then CPCG for area 3 is zero point 0.7, negative 0.7. This one, negative 0.7. So basically, all you have to do is look at this um, in the what do you call this one, in the table in the building code. There is that table that gives you the um, value of the CPCG. This one here. Where is it? Where's the table? I don't know. I cannot find it. But basically, you will see like this one here, and then it will have a value of all the CPCG coefficients, depending if it's load case A. Load case A is perpendicular to the ridge, and then load case B is if it's parallel to the ridge line. So it has different coefficient of CPCG. And then this one now is so for example, this is the PSF here, the conversion, but this is the KPA. So for one, this 0.35, if you look at here, 0.39. Let's check this. So this one, because they are using one in here, I said for some reason that I don't know, they are using one, and it should give the value of P is 0.39. Is it 0.39 here? Yeah, 0.39. And then area 2 is 0.68. 0.68. Area 2 is one here. 0.68, 0.39. See? So yeah, so that's it. Like if you just make like a spreadsheet, then it will be faster. But um, that's how it is calculated. Now, how you apply is we will discuss it right now. So let's see if we can copy paste this one. So you already know the coefficient. So let's talk about how it is being applied. Now for main wind force resisting system, like I said, the this is now a combination of the external wind pressure, the external and the internal. And this is where the plus minus plays a crucial role, like how you understand the unit and what it means. So, like I said, the the let's just draw another one. So if this is your frame, so if this is your frame, so your negative value for the pressure, this is negative is going that way, and then positive is good. So this is negative, this is positive. And then we're just talking about the external wind pressure first. So this is positive and this is negative. This is negative and this is positive. And then this is also negative and this is positive. Now in the internal pressure, you will also have uh, internal pressure you will have positive and this is negative, and then this is positive and this is negative, this is negative, this is positive, this is negative or positive, this is negative. Now when you analyze, say, windward direction from left to right, so assuming our wind is in this direction, what will happen is your frame, right? So your frame, let's just hide this one. So that's your if you notice the value here, um, one is positive, one is windward because it is going this way, and then area 2 here, like from the diagram, where's it? From the diagram, so this is area 1 here, area 2, and then area 3, and then area 4 on the back side or rear side, leeward side, I would say. So if that's the case, so one is positive, the rest is negative. So that means only one is positive based on the slope. So this is area 1, this is area 1, this is area 2, then this is area 3, and this is area 4. Now, if the wind is in this direction, that means this one is positive going. So this is positive, no, going towards the wall. Now, when you do the calculation, you will have to, it's either, if you know already which one governs, then that's fine. You can analyze it directly. But um, like I myself, what I do is I have a template because when we have a project, although this will be handled by a third party like the supplier, they will do the calculation itself. What I usually do, because when I design the foundation, there is no reaction yet because it takes like months to get the reactions from the manufacturer. What I will do is I will do a mock calculation. So I will model this one here, this frame, apply all the loads. Then I will have a um, if you notice in the software you have what we call this one, the load case, like auto generated, no? The auto generated load combination, but I don't use that one. I have my own, load combinations. I create my load combinations. Now in my load combinations, I will have, so this one is permanent. I mean, not permanent, but this is this won't change. Like the external wind pressure, if the wind pressure is this way, then that's the direction. But my first combination is, I mean, if this is symmetrical, uh, if this is symmetrical with respect to this axis, I mean, whatever is the shape here is the same as this one on the right side. That means that all you have to do is analyze it in one direction, and then whatever is the result in this analysis, if the wind is going that way, it will be the same if the wind is in this direction from right to left. But in my template, I separated the two combination because it's not always symmetrical. Sometimes it's different, especially if your frame is monoslope like that, right? So the wind force in this direction is different if the wind is in this direction because of the height difference between the two. If you have a monoslope, so that's why I in my template it's applicable to both like symmetrical and unsymmetric. But what I will usually do is assuming the wind is in this direction first. So this is my leeward, right? This is my leeward or windward positive, and then all other pressures are negative. Now my first combination is this one, positive, no? Positive plus positive. So first two combination is plus positive, positive. So you add the positive here and the positive here. I mean, what I mean is positive and positive is I will use the positive internal pressure first. So all positive. So this one will have a net value of going. Usually this is bigger than the internal pressure. So you will have a net, what we call this one, net positive pressure here, going to the right. And then right here, now, if you notice, this is negative and this is positive, but this will produce the big. By the way, you don't mix the two, right? So, for example, if you analyze the structure using a positive here, you don't have the option to use negative here. You have it's either use both negative or use both positive. You either apply the positive only, positive internal pressure, and then apply separately, and then um, make that a different load combination. So, for example, like I said, if you use positive here, then use positive all throughout. Then next load combination is negative. Then use all negative. This one. So this one, in this case, the negative internal pressure will be added to the positive external pressure. I'm not sure if other engineers would use the worst loading combination. For example, this one, you will use this positive and negative combination and then negative and positive combination, that I'm not sure. But in my load combination, I use either positive only in all side or negative only in all side. So in this design guide, it's probably 0.36, 0.68, 0.39 positive. Design conventions, select design cladding surface, therefore pressure. Design positive internal pressure. Yeah, looks like you apply it's either positive only or negative only. Um, yeah, right here. So this one is adding all negative pressure, and then this one is also adding all positive. So yeah, so yeah, again, um, let's clear this up first. So, so so again, this is positive, this is negative, this is negative, and this negative. This is positive. Now your first combination is you add or you combine the external pressure with the positive internal pressure, positive, 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 and positive. That's why it is smaller here. Or this one is you will get a net, but this one you will get a you will add no, the absolute value add here. Then this one is subtract, and then this one you also add because it's the same direction, and this one also the same direction. Now the next combination would be the all external pressure and then the negative internal pressure. So this case, this one will be added to the internal pressure. This one will now be subtracted. This one will be subtracted. This one will be subtracted as well. So, yeah, that is how the wind loads are applied to the pre-engineered building. So again, there is a limit with regards to the area. Now, in our situation, for example, this is a hip roof. So this is your ridge line. So trusses is usually spanned that way. Now, for example, residential houses back home, say this is a 4 meters only, and then this one is your spacing is say 2 meters spacing, no, for the trusses, because houses are small like back home. So if that's the case. So your tributary area, if you are designing this truss, analyzing this truss, now the difference is if this truss is no, when you design this truss to calculate the lateral force resisting system, say you design for the lateral load, then you will use the tributary now. Calculate the tributary if this one will be designed as a half of that. No, half of that. If this will be designed as a um, um, components and cladding or main wind force resisting system. But for designing the lateral force resisting system, you always use the MW, main wind force resisting system. But if you design the truss itself, that is where you consider now which one applies. Is it tributary area? So 2 times 4, 2 times 4, that's 8 times 8 square meters. Area, square meters. So this is 8 to square feet. This is what happens if you are now dependent on calculator. Square feet. So that's 10 square foot, right? Or no, this would be 2. That's 21. So the limit is 700. So when you design the truss, itself, then you have to use the components and cladding. So again, per code, the criteria is this one, 700 square meter. If your tributary area for that truss is greater than 700, then you are permitted to use the MWFRS, which gives you um, a smaller uh, this one forces. But in this frequently asked questions, it says, or the question is, when is a gable truss in a house part of the MWFRS? Should it also be considered, should be designed as components and cladding? What about individual members of a truss? So in the ASCII-7 design guide for wind loads, it says roof trusses are considered to be components since they receive load directly from the cladding. However, since a gable truss receives wind loads from more than one surface, which is part of the definition of the MWFRS, an argument can be made that the total load on the truss is more accurately defined by the MWFRS load. A common approach is to design the members and internal connections of the gable truss for CNC loading. No? When you design the members, while using the MWFRS for the anchorage and reactions to the truss with wall or frame. So basically, because it is worst case to consider CNC loading, because you can argue that which is true. So this is truss, but your purlins were designed for components and cladding forces. Then the truss is directly supporting that element which were designed using components and cladding. Then it should also be designed for components and cladding when you design the truss. But when you design for the anchorage right here, how you transfer the load to the supporting element, either beam and column, or also calculating for the lateral load that is contributed from your roof, then you have to use the MWFRS. So right here. So when designing shear walls or cross bracing, roof loads can be considered part of the MWFRS, because technically that will also give the maximum reaction for, or the maximum net lateral load. For example, the idea is, so if this is your truss, show me that's your truss. Now, if you noticed in the components and cladding, the diagram, right, it's divided. This is HUDs, and this is HUDs diagonally, and then there's a solid area. If you notice, this one and this side of the roof is the same. That means your pressure here, right? Your pressure in this area will be the same. If this is, say, for the sake of example, this is minus 10. This is also minus 10. Now, if you resolve this, so you have your resultant in that direction. This is also your resultant R, right? Resultant R. Now, you will typically, when you analyze it to simplify the calculation, is you will get the horizontal component at the same time the vertical component. So this is RV, this is RY, this is also RV, RH, not RY. So this is also RV, RH, and this is also RV. Now, RV components, which is fine, then that is now all up left. But if you notice, the RH cancel each other. So which one do you think produce a bigger lateral load? Because if you use components and cladding, this is now zero. Your horizontal load is zero. But if you are using the MWFRS, it's your roof, right? So this one is, although this is negative and this is also negative, but this is always, if the wind is in this direction, this is always lesser than this one here. So say, let us say in the calculation, what is 1? 2 is 0.99, 3 is 0.68. So this one here. So in this example, 0.68 at 0.99, right? So this is 0.99.68. Now, if you get the horizontal components and the vertical components, This is also vertical. This is also horizontal. If you notice, this is bigger than this one, right? So therefore, there will be a net forces in going this direction, right? That one. But the problem now is your if you design the forces here, if you consider now the wall, this will be acting in this direction, and then this is also acting in this direction. Now, if you notice, this now is negative, which will significantly, or not significantly, but it will reduce your lateral load because it will be subtracted from these forces now. Now, what I do usually, or not usually, always, is I will just neglect the contribution of these forces. So when I analyze, say, for example, a house, when I analyze a house, like say gable roof, I will neglect this in calculating for my shear wall in this. For example, this is our building, and then the wind is in this direction. So we are technically designing this wall here. Then I will not consider the roof because it will reduce my wind loading in this direction because of this, right? So I will not consider. But if you are calculating for a pre-engineered building, that's another story. Because if that's the case, if this is pre-engineered building, then you have to combine everything, like all of this, because it's one whole system. Compared to trusses, where the truss is different, and then you just apply the load at the top of the roof. So I don't. That's why I don't consider a roof if I design like a shear wall for residential house where the trusses are not integral with the vertical like the walls and on the columns. But for pre-engineered building, because this is single, basically like a rigid element, single one or single element, then that's the time I will consider all direction of forces. So I don't know how other engineers do it with regards to this one. I mean, this is given. It's the same for everybody. But on this one, I don't know how other engineers analyze this one. But to me, it's more conservative if you just neglect this one because it will reduce the unless you are investigating say, for example, investigating an existing structure where I mean, this would, determine if your structure fails or not. So, I mean, it really depends, but sometimes if the difference between the demand and capacity is really small, this will play an important important consideration. So it's really up to you. So I think this should um, sum up our discussion with regards to how the wind loads are applied to a structure. So again, if you are not sure, you can always look up the provision in the code. Like I said, this is from ASI 7. I would say just follow it. I would say it's been I mean, our codes back home in the Philippines uses Winload anyway, ASI 7 anyway. So I would assume the way it is worded in the National Structural Code, the NCP, that would be the same as this one. So again, there is no windward only and leeward only combination in wind loading. It always go together, like windward plus leeward. Oh, hey, here, by the way. So this is the load table that I mentioned for the primary structure. That's why in my spreadsheet I have this wind load primary because this is for the um when you analyze for the lateral yeah, for the when you design for the lateral force resisting system, it's either bracing or shear wall, whatever it is. This is the load that you use. But for the individual component, that's the time you use the, for example, if it's a liner, um, if it's a roof cladding, I have like Portlands, I have like end wall, wall girts, wall cladding, Portlands that are monoslope. So roof cladding, monoslope. So this different. I just find it because in this particular, you know, um, calculation, it's I'm just following whatever is shown in this design guide. So, but all you have to do, if for example, if you need Portlands is monoslope, is you just unhide that one, and then this is the calculation for the Portlands. So Portlands that are monoslope, this one. So that's different wind pressure, different. I mean, this the same zone, but different the way it is placed. Or this one here is, what is this now? So you have C prime, you have S prime, and then S prime, and then R is the, unlike the monoslope where you have um, two surface, like both sides of the ridge. But on this one, this is a monoslope, so that's um, single surface. That's why this bigger area is all R. There is no more S and C in the ridge line. But I'll just basically refer to this diagram here, and then you will have your coefficients. And yeah, just make a spreadsheet, and um, it will be easier next time. Well, when I do a spreadsheet, I always have I always do a manual calculation first, like by hand, and then I will make a spreadsheet out of that calculation. Then I will keep changing the value, then like run parallel calculation, manual calculation, then maybe 5 trials if the results are equal, different conditions, changing the slope, changing the area, changing the configuration if it's monoslope or um, gable or hip and gable. Then if the result remains like equal in both spreadsheet and by hand, then you can say that your spreadsheet now is um, correct. Because sometimes when I first start my spreadsheet, sometimes when I change the given values, the conditions, the result would be different. So if you will make a spreadsheet, I think for Canadian engineers, then maybe use make a spreadsheet out of this design guide so that you can check all your results if it's the same as this one. Or I'm sure in SS7 there are also design guides, especially this one, the wind load provisions for design guides for wind load, yeah, provisions of SS7. Then this design guide also have like sample calculations. Then when you make the spreadsheet, then make sure the answers or the results would match with the example provided or given in the design guide. So I hope it is clear now. And if you have questions, just comment, write your questions in the comment section, and I will try to address that one. Okay, bye.